Hello my dear friends. So welcome to another lecture in Tesla Institute of Physics, and if you like the videos of Tesla Institute of Physics, then do not forget to like, subscribe and share all the videos and press the bell icon so that you can get the notification of all the videos. Okay. So in last lecture we discussed about blackbody radiation and blackbody spectrum. Okay, and from the blackbody radiation or the blackbody spectrum, what we find? An wavelength at which energy is maximum gradually decreases with increase of temperature. Okay, and the area under the curve also increases. So that's why we find Wien's displacement law, Stephen's law, like different concepts. Okay, but the blackbody spectrum was still a mystery. Okay, a number of scientists came to describe the blackbody spectrum. Okay, some of the scientists failure to describe and some of the theories are accepted. Okay, so out of which one theory is Rayleigh and Jeans law. Okay, Lord Rayleigh and James Jean use the classical statistic concept in order to describe the blackbody spectrum. Okay, Rayleigh and Jeans use law of equipartition of energy in order to describe the blackbody spectrum. Okay, so as per law of equipartition of energy, the average energy associated with each mode of wave is equal to 1 by 2 kT. 1 by 2 kT. The average energy for each mode 1 by 2 kT. K is the Boltzmann constant and T is the temperature. Okay. So Rayleigh and Jeans first assume a cubical cavity black body of length, breadth and height equals to L. Okay, and they assume that when the radiation enters to black body, it makes a standing wave, it makes a number of standing waves. Okay, when the radiation enters to the black body, it makes a number of standing waves. Okay, so that they take the wall of the cubical cavity is made with non-zero conductivity. Okay, the wall of the cubical cavity is made with non-zero conductivity, so that when the standing waves or when the spectrum hits the wall of the cavity, it is reflected back and form standing waves. Okay, so in order to measure the total energy, okay, we have to first measure the number of modes of standing waves formed inside the cavity. Okay, and another things they also take that all the standing waves form their node point at the wall of the cavity. Okay, and the wall of the cavity are made with non-zero conductivity. If conductivity is non-zero, then what happens? The electric field at the wall must be 0. So that's why there is a boundary condition arises, which is, suppose I consider along x direction, x equal to 0 to x equal to L, that is the length of the boundary, and if the wall is non-zero conductivity, then electric field is 0 at the wall. Okay. So, what is the boundary condition? So, boundary condition is electric field is 0 at wall of the cavity, that is x equal to 0 and x equal to L. Okay. And when the electric field is 0, the standing waves or the spectrums when hit the wall of the cavity, okay, they reflected back, okay, like this. If a spectrum starts from one of the wall and it moves towards the another wall of the cavity, and when it strikes this wall, it is reflected back and it forms a standing wave. Okay. So, we have to measure the total modes of standing waves formed inside this cavity. Okay. So, in order to measure the total modes of standing waves formed inside the cavity, suppose we assume first the number of modes of standing waves that form in x direction. Okay. Suppose I take here x equals to 0 to x equal to L. Okay. And an important thing is that the length of the box must be greater than that of the wavelength of the wave. Okay. Length of the cavity must be greater than that of the wavelength of the wave, so that a standing wave can fit well inside the cavity. Okay. So, if I consider our first mode, okay, one mode of vibration, what happens? For one mode of vibration along x direction, L will be lambda x divided by 2. Okay. And if I consider two mode of vibration, then L equals to 2 lambda x divided by 2. And if we take 3 mode of vibration, okay, then L equals to 3 lambda x divided by 2, that is if I consider 3 mode of vibration. And if we take n mode of vibration along x direction, so L will be nx lambda x divided by 2. Okay. So, nx is the number of modes of vibration along x direction. Okay. And likewise, the spectrum formed along y direction and along z direction. So, we can take the values along y direction, along z direction will be L equals to ny lambda y divided by 2 and L equals to nz lambda z divided by 2. Okay. Now, the waves formed along x direction, y direction, z direction. Okay. But there is a possibility is that some of the waves also form in arbitrary direction. Okay. So, if the waves form in arbitrary direction, so what will be the value or what will be the modes of vibration? Suppose I consider some waves that form along the arbitrary direction. Okay. Some waves form along the arbitrary direction. Suppose I take this x, that is y, and there is a wave that form in arbitrary direction with making an angle alpha with x axis, beta with y axis and gamma with z axis. So, alpha, beta and gamma are the angle that makes the arbitrary wave with x axis, y axis and z axis. Okay. Suppose along x direction there will be 3 modes of wave along x direction, okay, and 2 modes of vibration along y direction. Okay, so there are two mode of vibration along x direction, that L equals to 3 lambda x by 2 and L equals to 2 lambda y by 2. Okay, wave along x direction, that will be 3 mode of vibration. Okay, and along y direction there will be 2 mode of vibration. Okay, so now let's join the node points. Okay, so if you join the node point, then this will be wavelength. Okay, this length is the wavelength that along the arbitrary direction, and suppose we take that wavelength as lambda. Okay, and along x direction the wavelength is lambda x, and along y direction the wavelength is lambda y. Okay, and if we measure the component of lambda x, along the arbitrary direction. So what will be the value? Lambda x cos alpha. The component of lambda x along arbitrary direction, if it makes angle alpha, then that is lambda x cos alpha, and component of lambda y along arbitrary direction will be lambda y cos beta. Okay, and we know the maximum value of cos theta, lies in between -1 to +1. Okay, so that's why lambda less than equal to lambda x. Okay, lambda the wavelength less than equal to lambda x. Okay, or lambda less than equal to lambda y. Okay, so what are the different components? So component of lambda x along lambda will be lambda equals to lambda x cos alpha. Okay, so that why lambda x equal to lambda divided by cos alpha. Okay, now the component of lambda y along lambda, that is lambda equals to lambda y cos beta. Okay, so that's why lambda y equals to lambda divided by cos beta. Okay, and like this we also can obtain the lambda z, that is lambda by cos gamma. Okay, so let's use lambda x, lambda y and lambda z in these respective values. Okay, and if we use the values of lambda x, lambda y and lambda z in the respective values and simplifying, we get nx equals to, okay, nx equal to 2l cos alpha divided by lambda. Okay, ny equals to 2l cos beta divided by lambda, and nz equals to 2l cos gamma divided by lambda. Okay, and square these three nx, ny and nz, then make a addition. What we get? Nx square plus ny square plus nz square, that equals to 2l upon lambda square into cos square alpha plus cos square beta plus cos square gamma. Okay, so as per the Pythagoras theorem, cos square alpha plus cos square beta and cos square gamma, that is 1. The value of cos square alpha, cos square beta and cos square gamma equals to 1. So nx square plus ny square plus nz square, that equals to 2l upon lambda whole square. Okay, so that implies to nx square plus ny square plus nz square under root equals to 2l upon lambda. Okay. So, till now we are analyzing the modes in a Cartesian coordinate system. Okay. We are taking all the modes of vibration in Cartesian coordinate x, y, z. Okay. So, let us analyze the modes in a coordinate nx, ny and nz. Okay. So, if we consider a coordinate nx, ny and nz. Okay. In nx, ny and nz coordinates, all the modes are represented by dot. Okay. All the modes represented by dot. Okay. And what is the aim of measurement? We want to take the measurement of the number of modes formed inside the cubical cavity. Okay, because average energy associated with each mode is 1 by 2 kT. So, in order to measure the total energy, we have to first measure the number of modes inside the cubical cavity. Okay, so that is why when we represent the total modes along nx and ny and nz coordinate, all the modes is represented by the points. So, the points represent the mode of vibrations. Okay. So, now if I take a sphere of radius rho, in nx, ny and nz coordinate, then we can say this portion of the sphere is 1 by 8th. This portion of the sphere is 1 by 8th of the total sphere. Okay. So, now if rho is the radius of the sphere, in nx, ny and nz coordinate, then we can write rho equals to nx square plus ny square plus nz square root over. Okay. As like we write r square equal to x square plus y square plus z square root over, that is the radius of the sphere. So, rho equals to nx square ny square plus nz square root over. Okay, and that equals to, if you compare these two equations, and that equals to 2L upon lambda, Okay, and if I assume or if we convert lambda in terms of frequency, then lambda equals to C upon nu. Okay, nu is the frequency. Okay, so that is why rho equal to 2L nu divided by C. Okay. So, now let us measure the mode in a small volume range, in which the mode of the vibration varies with a small frequency nu plus d nu. Let us analyze the number of modes that form in a small volume. Okay. Small volume. Okay, and that is why we take another sphere, okay, whose radius is rho plus d rho. Okay, the radius of sphere is d rho, and the thickness, here we get the thickness that equals to d rho. Okay, so now let us measure the volume associated by this region. Okay. So, as we know, this region is 1 by 8th of the total sphere. Okay. And in order to measure the volume, we know if we multiply, if we take the concept of a square, okay, if we take the concept of a square, in case of square, if we multiply the base area, with the height, if I multiply the base area with height, then what we find? Base area into height gives the volume. Okay, we use the same concept here. Okay, so in order to measure the volume of the spherical region associated in nx and ny plane, okay, the volume of the region associated with nx and ny plane, we simply multiply the inner surface area with the thickness, and if the inner surface has a radius rho, then its surface area is 4 pi rho, okay, and the thickness here, that is d rho, and this portion is 1/8 of the total sphere. Okay, so in order to measure the number of modes, okay, we can also measure the total volume associated here, total volume associated with a small region in which the spectrum varies with a small frequency range nu to nu plus d nu. Okay, so the volume associated with this region will be, so take here rho equal to 2L by C, right here rho equal to 2L nu divided by C. Okay, so now let us measure the volume. Total volume equals to total number of standing waves, or total number of modes, within a frequency range nu to nu plus d nu. Suppose that we represent the total number of modes as n nu d nu. Okay, so n nu d nu equals to 1/8 of the sphere, or 1/8 of volume of this region, and the volume of this region is 4 pi rho square d rho. Okay, 4 pi rho square d rho. But for each spectrum there are two mode of vibration. Okay, for each electromagnetic spectrum there are two mode of vibration. Okay, so that's why actual number of standing waves, or actual number of here we can mention, for each electromagnetic wave, I represented electromagnetic wave, there are two modes of vibration. Okay, so that's why actual number of standing waves, actual number of modes will be twice. Okay, actual number of modes equal to n nu d nu equal to 2 times of 1/8 into 4 pi rho square d rho. Okay, and that equals to pi rho square d rho. Okay, so here the rho value is 2L nu by C. Okay, so if we take the frequency changes with the change of the radius, so d rho equals to 2L upon C into d nu. Okay, so what will be the value of n nu d nu? So n nu d nu equals to pi 2L nu upon C square 2L upon C into d nu. Okay, so that equals to 8 pi L cube nu square divided by C cube d nu. 8 pi L cube nu square divided by C cube d nu. So that will be the actual number of modes inside the cubical cavity. Okay, that will be the actual number of modes inside the cubical cavity whose frequency varies in a small range nu to nu plus d nu. Okay, so now as per law of equipartition of energy, we use the concept of law of equipartition of energy. Okay, so as per law of equipartition of energy, energy associate average energy for each mode of vibration. Average energy for each mode of vibration, each mode equals to 1 by 2 kT. Okay, but we know when electromagnetic wave propagates, there will be two, for one mode there will be two different, when electromagnetic wave propagates, there are two different mode of energy. This is the energy, and energy has two different modes. One is kinetic mode and another one is potential energy mode. Okay, one mode is kinetic energy mode and another one is potential energy mode. Okay, so the total energy, okay, so the total energy for each mode of vibration, total average energy, okay, so total average energy for each mode, okay, equals to kinetic mode plus potential energy mode. Okay, so that will be kT. Okay, so that will be the total average energy associated with each mode, and this is the total number of modes. Okay, and we want to measure the total energy inside the cavity. Okay, and this is the energy for each mode and this is the total number of modes. Okay, so if we multiply these two factors, then we can find the total energy associated with the cubical cavity. Okay, so the total energy, total average energy, so total energy in a frequency range, nu to nu plus d nu is, suppose I represent as E nu d nu, that equals to number of modes into energy associated with each mode. Okay, and number of mode is 8 pi LQ nu square divided by CQ d nu into kT. Okay, so that is equals to 8 pi LQ nu square kT divided by CQ d nu. So this will the energy associated inside the cubical cavity or inside the black body radiation. Okay, so now if we multiply or if you want to measure the energy density, okay, then energy density is energy per unit volume, and we consider the cubical box. Okay, so for the cubical box, what is the volume? So volume equals to LQ. For cubical box, V equals to LQ. So what will be the energy density? Energy density, suppose I take that is U nu d nu. Okay, so that will be total energy divided by volume, total energy divided by volume. So that equals to E nu d nu divided by LQ. Okay, so here there is a LQ term. If you divide this, so that will be E nu d nu equals to 8 pi nu square kT divided by CQ d nu. Okay, so 8 pi nu square kT divided by CQ. into d nu. So, this is called Rayleigh-Jeans law. Okay, but the important thing about the Rayleigh-Jeans law is that the Rayleigh-Jeans law failed to explain the blackbody radiation. Important thing is that the Rayleigh-Jeans law failed to explain the blackbody spectrum curve. Okay, so in our next video we discuss why Rayleigh-Jeans law failed to explain blackbody spectrum. Okay, and that failure of Rayleigh-Jeans law is known as ultraviolet catastrophe. Okay, so next video we discuss about ultraviolet catastrophe. Okay, so I think all of you should get an idea about the Rayleigh-Jeans law. Okay, so if you like the class, then subscribe the channel and press the bell icon, and if you like this lecture, then share and subscribe. Okay, thank you.